The next presenter is Zhang Ziyu. Zhang Ziyu is a second-year PhD student at Fudan University. His research focuses on network hardware design and programmable networks. Today he is going to present vPIFO, sorry.
So, okay, thanks for the introduce. And good morning, everyone. My name is Zhiyu Zhang, and I'm from Fudan University. And today, I'm glad to share our paper entitled vPIFO. It's about utilizing the concept of virtualization to realize hierarchical programmable scheduling. And this is a joint work with Pengcheng Laboratory. Packet scheduling is a crucial component in ensuring quality of service, and a lot of algorithms have been designed for different application goals. However, few of them are put into use on chips due to high hardware costs. So we actually need a programmable packet scheduler. PIFO is a popular model in recent years to realize programmable packet scheduling. And in the PIFO model, each packet is tagged with a rank by the rank function. And different algorithms can be realized by changing the function. And the packets were stored in a priority queue with ascending ranks, with the packet having the smallest rank going first. However, in multi-tenant data centers, the demand for network performance becomes more complex, with each level having its own performance goal. For example, at the application layer, some applications desire high priority, and this calls for the use of the SP algorithm. And at the tenant layer, we might want to distribute bandwidth among tenants, and which calls for the use of the WFQ algorithm. And finally, at the tenant group layer, and the VIP group need higher priority than normal group, and requiring the use of the SP algorithm too. So as a whole, these demands from different layers exist simultaneously. So it becomes clear that MTDC actually need a hierarchical scheduling algorithm, and which a single PIFO can't realize. PIFO tree composed of multiple PIFOs can realize hierarchical algorithm, and the hierarchical scheduling requirements we just discussed can be realized by the PIFO tree on the right. However, multi-tenant data centers are inherently dynamic. For example, if tenant 3 want to upgrade their service, and the whole scheduling requirements also change, and in this case, the number of required PIFO queues changes, the previously configured PIFO tree can no longer meet the demands. So we can see that the existing PIFO tree can't adapt its number of PIFO queues and or connections, and leading to a lack of structural programmability. So to address this issue, we propose the concept of virtualization. By multiplexing a physical PIFO, we can logically build any numbers of PIFO instances, and to enable programmable hierarchical scheduling. Based on the concept of PIFO virtualization, we provide the following framework. First, we abstract the hierarchical scheduling requirements into PIFO instances. Next, we manage PIFO instances in the hypervisor and maintain their relationships. And finally, the physical PIFO completes the ranking operation by the PIFO instances. So to realize this framework, we face 3 main challenges. First, in terms of hardware design, how to design a multiplexable physical PIFO. Next, in terms of runtime management, how to allocate physical PIFO resource to logical PIFO instances. And finally, in terms of initial configuration, how to express hierarchical scheduling algorithms using logical PIFO instances. So okay, let's start with challenge 1. How to design a multiplexable physical PIFO. And we take a look at the current designs of the physical PIFO. And among various related work, our previous work, BMW stands out with the highest scalability by supporting over 100K flows. And thanks to its tree structure, the amount of data involved in single operation is at the O log n level. Compared to other ON level works, BMW tree has the smallest context. Next, let's review the hardware architecture of BMW tree. And in BMW tree, the packet priority is stored in SRAM, and the ranking processing unit, RPU, loads data from SRAM, performs ranking, and then store it back to SRAM. So for the push operation, the push command starts with RPU1, executing the sequence of load, rank, and store. Once the command is completed in RPU1, it is then passed on to the RPU2. And this process continues with each RPU handling the push command in turn. And the push operation is considered complete when all RPU has finished its push command. So for the pop operation, it is similar to the push operation, and the only difference is that in the pop operation, each RPU, after each RPU completes the load and rank, it must wait for the next RPU to finish its load, rank, and provide the data. After that, it can perform the store. So we can see that in BMW tree, the context refers to the data in the RPU. And this means that as long as we can dynamically load and store data, the RPU can serve different PIFO instances. So okay, for the storage part, we combine the data of multiple PIFO instances together, like that. So our data placement strategy focuses on balancing the SRAM size by placing the root node of the PIFO instance on different SRAMs as much as possible. And next, for the ranking part, we arrange the original PIFO sequence into a ring. So with these modifications, we can now serve multiple PIFO instances simultaneously. And in this picture, the different colors represent different instances. And now we can see that they can perform operation on a single physical PIFO. So okay, now we have multiplexable physical PIFO, which we called PIFO engine. But how to allocate it to logical PIFOs? Sorry. For example, on the left, we see many operations arriving. So when faced with such operations, which ones should be processed first, and how to avoid conflicts between them? So to efficiently solve this problem, we should first classify these operations. So we introduce operation queues. And operations are queued according to the SRAM of respective PIFO instance, like that. And this aligns with our data placement strategy. And each operation queue is a FIFO. So every time we dispatch operations, we select from the head elements. And in this, we use a greedy algorithm to maximize RPU utilization. And the specific detail of the algorithm can be found in the paper, where we provide the analysis and experiments to support its efficiency. So, okay, now we can allocate logical PIFOs. We call this module PIFO Visor, like hypervisor. But how to express hierarchical scheduling algorithm using logical PIFO and using PIFO-Visor. So for complex hierarchical scheduling requirements, we desire a more formalized expression. Therefore, we introduce scheduling description language, SDL. And the SDL code is compiled and to generate configuration generation to the PIFO-Visor. And after configuration, PIFO-Visor can convert hierarchical requirements to PIFO instance operations. So now we have addressed the 3 challenges posed, and by combining PIFO-Visor, PIFO engine, and SDL, we have presented the vPIFO system. Overall, vPIFO works in 2 stages. First, there is the initial stage, where we set up the hierarchical scheduling algorithm. And next, there is the runtime stage, where we perform the scheduling based on the setup. In the initial stage, we start by parsing the hierarchical requirements written in SDL to virtual PIFO instances. And next, we generate the configuration table and provide them to the PIFO-Visor, PIFO engine, and package transaction. In the runtime stage, the incoming packets are ranked and then passed to the PIFO-Visor, which generate PIFO corresponding PIFO instance operations. And then PIFO-Visor selects some operations and then hand them over to the PIFO engine for execution. As a whole, the SDL and its compiler are realized in software, and the PIFO-Visor and the PIFO engine are realized in hardware. So finally, we perform simulations using S3 and do prototype tests on FPGA and ASIC. And the simulation were set up to see how hierarchical scheduling requirements, hierarchical scheduling algorithm affect the flow completion time. And meanwhile, the prototype tests were done to check the performance and resource consumption. In the simulation, we construct a 4-level hierarchical scheduling algorithm and consisting of 100 tenants. And the scheduling were performed across tenant group layer, tenant type layer, tenant layer, and application layer. And we measure the FCT of the highest priority tenant. So in the PIFO scheme, only one physical PIFO was used and requiring ranks at different layers to queue together. So as a result, the highest priority tenant was not actually prioritized in scheduling. And in contrast, vPIFO also used only one physical PIFO, but could logically build multiple PIFO instances and allowing ranks at different layers to queue separately. So the result shows that vPIFO achieved a 10-fold improvement on FCT. And in the prototype test, in the graph, the horizontal axis represents the number of instances that vPIFO can virtualize. And meanwhile, each line represents the capacity of one PIFO instance. So the original PIFO scheme, without virtualization, can support 4,096 flows and at a frequency of 50 megahertz. In contrast, vPIFO can achieve even higher priority while virtualizing multiple PIFO instances. And in the graph, the red dots represents a config that vPIFO sustains 100 gigabits per second line rate and supporting 122 instances, each with a size of 340 flows, and in a 4-level hierarchical scheduling. So and next, in terms of resource consumption, vPIFO demonstrates excellent scalability by supporting up to 24 instances, and each with a size of 5,460 floats and consuming only 11.42% of the lot. And in the ASIC result, vPIFO can reach 600 megahertz, and which corresponds to 400 gigabits per second in 6-level hierarchical scheduling algorithm, and vPIFO supports over 128 instances and more than 100 floats per instance while occupying less than 3% of the chip area. So, okay, finally, in conclusion, vPIFO is the first hardware packet scheduler to support programmable hierarchical scheduling through virtualization. So, okay, that's all. Thank you, and I'm glad to take any questions.
Thank you.
Hi, I'm Rulan from Xiamen University. My question is, do we really need a new language to design a new language for scheduling specification? I mean, for instance, Linux already has QDisk, which lets us describe similar hierarchical policies. So wouldn't it be easier to let users use this language to express their requirements? Why we need to design a new language, your SDL language?
So okay, that's really a good question. And the main purpose of we design the SDL and its compiler is to automate the configuration of vPIFO. As we mentioned earlier, so if we want to use vPIFO for expressing hierarchical scheduling requirements like this week, we need to correctly write the operation table to the three components, like PIFO-Visor, PIFO-Engine, and the package transaction. So while vPIFO can virtualize one physical PIFO to multiple instances, it also needs someone to tell him that how many instances it needs to create and how the instances to connect to each other. So although, as you say, there are many languages can describe the hierarchical scheduling algorithm, but their compilers can't provide the data the vPIFO need. And in fact, the currently SDL's syntax is relatively simple, and we are developing it and to eventually present it as a extension of the P4 language.
Thank you. I see.
Okay.
Thanks for sharing. I'm Yingxing from Zhejiang University. I'm curious if your systems can support dynamic policy updates. It seems requiring all policies to be available for compilation. This may be a limitation in faster changing cloud environment.
Okay. So as you say, supporting runtime update is actually an important feature, and currently vPIFO doesn't support this function. So in vPIFO, if you want to also this fig, if you want to change the hierarchical scheduling algorithm, you need to reconfigure the vPIFO. But in fact, with other existing technologies, if you want to achieve this, you might even to redesign the chip. And currently we are working on enabling vPIFO to support this feature. And as we can see that, the key idea vPIFO to express hierarchical scheduling algorithm lies on to to the 3 tables, and it means that as long as we can change these tables runtime, we can change the algorithm in the at runtime. So clearly, it's achievable. So it just needs some engineering effort. So is that clear?
Oh, okay, thank you.
Okay. In the interest of time, maybe we should move on to the next person.
One simple question.
Okay, sure.
So my name's Alex Francich. I'm with UC San Diego, and I'm wondering if you can speak to the relationship between the clock frequency and the packet rate that your scheduler supports.
So okay, that's a. In fact, as we know, if you use more complex algorithm, it actually needs more step to do just one scheduling, and
Yeah, maybe we should move this offline. Yeah,
okay.
thank you. Thank you.
Okay.
Sorry.